Okay, welcome everyone to the second to last lecture of the course. So I'm hoping to finish all of the material course-wise today, fingers crossed. And then I'm going to open it up to, well, I guess a free form, I guess, so to speak, of exam review or any other questions you have in the course. Now, if I recall correctly, I thought I had, oh, we might have to take a break halfway through. I had some practice questions for the previous unit, the wave nature of light with the diffraction and all that stuff. I had some practice questions set aside. It does not look like I've uploaded them to the OneNote folder. So whenever we reach the end of this lecture material, I might have to pop out and give you guys a 10-minute break or something in the middle, like we usually do in lecture or in-person classes, and upload them so we can continue practicing that way. But good news is today we should be at the end of the new course material. So we should have some time to practice the wave nature of light at the end of today's lecture. And then all day tomorrow, 2 hours of tomorrow's lecture, we can do course review. So I'll come to lecture with the past exams uploaded. That you can find the past exams online on the U of T library website. So I'll just have them uploaded here. So if someone wants to say do question blah 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 from 2018, you know, I'll have it primed and ready to go. But if you have your own questions from your own studying, tomorrow is exactly the time and exactly the platform to ask them. Okay, without further ado, let's get back to, oh, I should really ask before we jump into it, are there any outstanding questions from yesterday's lecture before I forge ahead? Yesterday's lecture, we introduced electromagnetic radiation, and we described that light is in fact a subset of the electromagnetic spectrum. What we call light, what humans call light, is actually a very small spectrum of what human eyes are able to see. So human eyes are able to see wavelengths between 400 and 700 nanometers. And this corresponds to a frequency in and around 10 to the 14, kind of 10 to the 15 hertz in that sort of region. But the electromagnetic spectrum is huge. And below red light, we call infrared, and you know, that's what we feel as heat. You know, we get that from flame or fire or the sun. And then below infrared is microwave, and your microwave oven uses microwaves to jiggle water molecules. Your cell phone also uses microwaves to communicate. And then below that even, we have radio and TV satellite signals. And we also talked about yesterday how radio waves, their wavelength is on the order of magnitude of, you know, 1 to 10 meters. And that's sort of the size of you as a human and or your car. And 1 to 10 meters is a relatively large range. So, you know, when you're listening to the radio, just picture in and around you, you have a wave that is a wavelength that is in and around a meter or two long. And that is a human body. So I think that's just really cool. You know, we think of these sort of invisible things as microscopically small because we talk about electrons and charges quite a bit. But, you know, radio waves, things we listen to when we turn on the radio, they're not small. They are, in fact, quite large in terms of wavelength, which I think is just really, really cool. So this is where we left off. Were there any questions before moving forward? I'm going to open the chat for for half a minute or so, give you a chance to ask anything from any homework questions you were doing yesterday from the textbook. I am assuming students are having enough time and, you know, prioritizing doing some little bits of homework every day. No, okay, nothing's coming through. That's fine. I thought I would just give everyone the chance to ask before we forge ahead. Okay, so if there's nothing further, I want to jump into delving a little bit deeper into why we call it an electromagnetic wave. And this is super cool, but it is a little bit advanced. So if you're getting confused by a description here and you're just not interested, you can tune out for a little while and maybe come back in when I show the video that's just below here. But, you know, if you are interested and eager to learn and expand your brain a little bit, you know, give it a good old college try to understand kind of what's going on here. So we do know that it's electromagnetic radiation. I told you last lecture that we have a combination of a sinusoidal electric field in conjunction with a sinusoidal magnetic field. And they happen together and they oscillate in phase with one another. Why is this the case? Why can we use our knowledge of physics, and well, I'll give you the hint, Maxwell's equations, to predict why we have specifically both? That you can't simply just have an oscillating electric field without also having an oscillating magnetic field. The two are inseparable. Let's see why this is the case. So let's first start with looking at Faraday's law. So Faraday's law, you're used to seeing as the electromotive force equals the negative derivative of the flux with respect to time. Okay, well, if you recall, the electromotive force is measured in volts, and the electromotive force is very similar to V equals E over D. Sorry, that's not true. E equals V over D, or V equals ED, E times D. So the electromotive force, we use in this class, we use a symbol curly E and then MF for EMF, but it's actually calculated with that integral. And you may recognize that integral from the beginning of the semester, where I showed you all of Maxwell's equations all in that chart there. And the flux, well, the flux, you might remember, is B times A times cos theta. But this BA cos theta assumed that the B field was constant, the A was constant, the theta is constant. You know, there's a lot of very idealized situations that went into the flux equaling BA cos theta. In real life, well, in real life, in more general terms, the flux is actually given by B vector dot product dA. And this was a very similar notion to what we did with the electric field. In Gauss's law, we had integral E dot dA, and that was the electric flux, how many electric field lines are going through a surface. Here is how many magnetic field lines are going through a surface. And then we just take the derivative of that. So what you're looking at here is more of the calculus rendition of Faraday's law. Now, in the context of electromagnetic field propagating forward, what we have here is our area is not changing. Really what's happening is our B field is oscillating, right? Our B field is a sine wave. Or actually, I guess what I'm trying to show you is why the B field is a sine wave, more specifically. So let's not jump to conclusions here. But it's the B field that is moving forward, right? Like a ray of light travels forward. So it's the B field that's moving with time. Our area is not changing with time. So all I'm doing here is I'm pulling the B value out of the integral. So I get dB by dt. And then the double integral of dA is just A. Right, so the integral of d area is just area, in the same way that when you use, let's say, u substitution in calculus, and you swap out all of your x's in terms of u's, you have blah 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 du. Well, when you integrate du, you just get u. Same thing here. When you integrate dA, you just get A. So that's where this A came from. So here we see that we get the integral of E dx is equal to the negative derivative of B with respect to time. And yeah, there's an A there, but A is sort of constant, so I don't really care about that. So whatever the B field is, we take the derivative of it with respect to time, and that will give us the integral of the electric field. So if we want to then find the E field, we would have to take the derivative of that answer, right? Now, that's one of the two equations. The second equation is Ampere's law. Ampere's law says the integral of B dx equals mu naught times the enclosed current. Now, I'm that's fine for this class. I sort of expanded that just a little bit, and you sort of got a taste of that in the pre-lecture video. You kind of saw the expanded Ampere's law just a little bit. Here, the current can also be represented as a varying E field with respect to time. You know, if you've got moving charges in a wire, then each of those individual charges, I mean electrons, will be emitting their own electric field, and as they move, they are bringing their electric field with them. So that's an electric field that is changing with respect to time. So this is another way to represent. It's a more complicated, more general way to represent Maxwell's equation, Ampere's law. Now here, I did the same trick. I pulled E out into the derivative, and then the second integral of E, or sorry, the second integral of A is just, well, sorry, the second integral of dA is just A. So that's where the A comes from. So here, our second equation says the integral of B dx is going to equal 1 over the speed of light squared times the derivative of E with respect to time. Oh, times A, right? Stupid A. The A's will cancel, as you can see. The A's in both equations. So whatever we have for our A field and our B field, not A field, our E field and our B field, they have to satisfy both of these equations at the same time. This is like saying two equations, two unknowns. Now, in high school, you learn about, what do they call them? Systems of equations. I think that's the math term for them. But I mean, the phrasing, two equations, two unknowns, you're sort of introduced to this in high school. And there's sort of two ways to do it. There's substitution and elimination. And we can actually do something very similar with these two equations. We can do substitution and elimination, but we just need some pretty advanced calculus to manipulate them and to do substitution and elimination. So I don't want to go through in any fashion the complicated solving of these two equations, because this is definitely fourth year physics if we jump into that realm. However, I want to show you something. Let's just cancel the A's for a second and ignore them, because they're in both of the equations anyway. So here, we have to think to ourselves, an electromagnetic wave is going to have a B field and an E field, and we want to know what the structure of those are. Why are they sinusoidal? Why do they both have to be present? Why are they both there? Well, let's look at this. If B was changing uniformly, and if you recall, up until now, all the questions we've been doing assumed the B field was changing uniformly, meaning it was increasing at a constant rate of, I don't know, 0.5 Tesla per second, or something along those lines, right? If the derivative of the B field is constant, then that means the integral of the E field is constant. And if the integral of something is constant, then that means that thing itself is zero, right? Because you can say if the integral of f dx is equal to a constant, then f equals the derivative of a constant, and the derivative of a constant is zero, right? So that's a notion that we borrow from calculus. So if you have a uniformly changing B field, you do not get an E field. Your E field is zero, and this is predicted by Faraday's law. However, what happens if the derivative of the B field is sinusoidal, meaning some sort of sine wave? It could be a sine wave, it could be a cosine wave. It doesn't really matter which one is which, because one is just a phase shift of the other one. Now, if the B field is changing like a sine wave, then the derivative, for sake of argument, let's just say the B field is a cosine. Okay, so say the B field is a cosine. Well, what's the derivative of cosine? Sine, right? So dB by dt would be sine, and same idea here. We would have the integral of f dx, or I guess we would have e dx, would equal the derivative of cos dt, which would be sine, and then to find e would then be the derivative of sine, which would then be back to cos. So Faraday's law says, well, if you have a non-uniformly changing B field, then you're going to induce not only a non-zero E field, but you're going to induce a sinusoidal E field. So if you have a sinusoidal B field, Faraday's law says you will naturally induce, you have to induce, mathematically it has to be there, a corresponding electric field that is also oscillating in a sinusoidal fashion. And Ampere's law, we have to say, okay, well, that's a solution for the first equation. Does that solution fit with the other of Maxwell's equations? Well, we look, we say, okay, well, we've already figured out from the first equation that the E field is a cosine. So we assume that this one is a cosine. Well, the derivative of a cosine is sine. So d of cos would equal a sine wave. And this is going to equal the integral of b. So then to find b, it would be the derivative of sine, which would then again be cos, which fits because we assumed b was cos. So it looks like if you assume this function to be your B field, then this satisfies both Ampere's law and Faraday's law simultaneously. And that's the key here. If you remember from grade 10 math, when you're solving systems of equations, whatever solution you find for x and y, it has to hold for the second equation as well. So it looks like B is a cos kx plus omega t. So it's a function of both space and time. I don't want to get in, well, we will get into that a little bit later in this lecture. And this actually will induce a solution for the E field that is, well, I really should have said B here, B naught. This is going to be E naught cos kx plus omega t. So the math shows that if you have a sinusoidally changing B field that has angular frequency omega and spatial frequency k, which is 2 pi over lambda, then you're going to induce an E field that is oscillating exactly the same way, perhaps a different amplitude, but exactly with the same frequency. So that's why when you see pictures of electromagnetic waves, they travel together because they have to oscillate together, and they travel at the same frequency together. And it's because of this coupling, this is what we call coupling. This is what we call coupling. Because of Faraday's law and Ampere's law, the electric and magnetic fields are actually coupled. And it just so happens you cannot have one without the other one. And that is just groundbreakingly revolutionary. When you have electrostatics meaning electricity that is not moving, then absolutely you notice nothing about magnetism. And we use that with Gauss's law. We analyze Gauss's law with stationary charges and charged spheres and, you know, a long charged tube and all this other stuff. And magnets that are not moving, same thing. Magnets that are not moving, we noticed nothing about electricity. It was just stationary magnets and the B field lines had to come home. That's in Maxwell's second equation. But as soon as anything starts moving, either a magnet starts moving or charges start moving, as soon as anything starts moving, these two things actually become the same entity. There is no such thing as electrodynamics. There's no such thing as magnetic dynamics. There's only electromagnetism together. As soon as things start moving, it's electromagnetic dynamics. You cannot separate one without also having the other one. And that is just remarkable. And just to put this into context for you, if you recall from the pre-lecture video, and we're about to see another short video here to help sort of explain this, that was only rectified with Einstein's theory of special relativity. Now, for context, I really want you to appreciate this. Einstein's theory of special relativity was published and founded in the relatively early 1900s. Okay, now think about how recent that is. That's about 100 years ago. And I know 100 years seems like a lot, but I mean, think of how old civilization is. I mean, Newton was, 400 years old or 200, whatever. And then Galileo was even before him. Like when we were studying things in 136, we were studying what we call classical physics. And that was from 200 to 400 years ago, sometimes even before then. The ancient Greeks were even studying aspects of physics as well. Those are thousands of years old, okay? Compared to all of this and compared to where you are and where we are in our civilization and our lives, the early 1900s, like your grandparents were likely, if they're still around, were likely around for this discovery. I know my grandmother, if she were still around, I think she was born in like 1908 or something like that. She would have been around in a time when, magnetism was known, electricity, well, there was electricity in cities and towns and stuff. However, this sort of field of physics just did not exist. So this is new. I know it doesn't feel new because all the textbooks talk about it and it's well documented online, but it is new that the human scientists have really only been investigating this for, a small number of generations. You could probably count the number of generations on one hand. We haven't even crossed over to the second hand of generations yet from the discovery of this. So, in the grand scheme of things, you guys are still one of the few people in the world to have ever be exposed to this. I mean, you're so close to the discovery of electro being coupled with magneto that, I know you guys don't appreciate it at the time because, you're in first year, you're just trying to get through this class, but I cannot drive this home that, how recent of a discovery this is. And it is just absolutely mind-blowing to me, partially because we've been desensitized. I mean, we live in such a technological age now. I mean, the internet was unfathomable even 30 years ago, hardly. Household internet 30 years ago was a laughing joke. They would have never thought that would have been a thing. And now we can just speak to our room and ask Siri or Google or Alexa, what the weather is like outside. Even that's unfathomable, but that perhaps has desensitized us to how the magnitude of importance that this is. But this is such a fundamental breakthrough in physics that this is not going to come around again in any of our lifetimes, probably ever. And you have been within 100 years of its discovery. So that is something that I really wanted to make sure I outlined for you guys. And whether or not you appreciate it at the moment, I can't help, but I really do hope that you can appreciate that Maxwell's equations. James Clerk Maxwell, I mean, he was around in the mid 1900s, and that's how new this is. It's really, really new and really, really amazing. So anyway, I hope you just appreciate that. Again, if you got lost in the math, that's okay. I just want the take-home message to be that they're coupled. They're coupled. You cannot have a changing magnetic field without also having a changing electric field. You have to have one when you have the other one. Anyway, here's another video that sort of explains why we had to wait for Einstein to sort of couple these two together. And it was Einstein's theory of relativity that actually explained that the magnetic force and the magnetic field is actually a result of a change of reference. It's actually a result of relative motion. So one could actually argue, after watching this video, you'll see, one could actually argue that the magnetic field doesn't even exist. The magnetic field is actually an electric field viewed from a different frame of reference. And we studied frames of reference in 136. So anyway, watch this video, and I hope it helps.
Only a few elements can be permanent magnets: iron, is 1. Copper is not. But if you pass an electric current through any metal, it becomes a magnet, an electromagnet. But how does this work? Well, strangely enough, it's a consequence of special relativity.
Special relativity is the fact that in our universe, length and time aren't absolute. They're perceived differently by observers moving relative to each other, hence relativity. For example, if you measure carefully enough, you'll find that time passes slower for observers moving relative to you. Hey Derek, when did you last shave?
6 hours ago. Actually, it was 5 hours, 59 minutes, and 59.99999999999 seconds.
And moving objects are also contracted in their direction of motion.
You're looking slim, only in your frame of reference. So when an object is moving relative to you, it actually takes up less space than when it's not moving. And even though this effect is obviously way tinier than we've shown, length contraction is what makes an electromagnet work. Picture a copper wire. It consists of positive metal ions swimming in a sea of free negative electrons. Now the number of protons is equal to the number of negative electrons, so overall the wire is neutral. So if there were a positive charge or positively charged cat nearby, it would experience no force from the wire at all. And even if there were a current in the wire, the electrons would just be drifting in one direction, but the density of positive and negative charges would still be the same, and so the wire would be neutral, so no force on the kitty. But what if the cat starts moving? Imagine for simplicity that the cat is moving in the same direction as the electrons with the same velocity. Well now, in my frame of reference, the wire is still neutral, and so there should be no force on the cat. But consider the same situation in her frame of reference.
In the cat's frame of reference, the positive charges in the wire are moving, so according to special relativity, their separation will be ever so slightly contracted. Also, from this perspective, the electrons aren't moving, so they'll be more spread out than before. Remember, objects take up more space when they're not moving than when they are. These two changes together mean there's a higher density of positive charges in the wire, so it's no longer neutral, it's positively charged, which means that the positively charged cat will feel a repulsive electric force from the wire.
But in my frame of reference, this seems mysterious. There's no force on a stationary charged cat, but a moving cat is somehow repelled from this neutral wire. How do you account for that force? Well, we say it is the magnetic force, and that's mainly because a wire with current in it deflects nearby magnets. So really what this experiment shows is that a magnetic field is just an electric field viewed from a different frame of reference. In the cat's frame of reference, it is repelled from the wire due to the electric field created by the excess positive charges produced by the effects of length contraction. In my frame of reference, the cat is repelled from a neutral wire due to the magnetic field created by the current flowing in the wire. So whether you see it as an electric or a magnetic field just depends on your frame of reference, but in either case, the results are the same. So an electromagnet is an everyday example of special relativity in action. Now that might seem crazy, since electrons drift through wires at about 0.00000000001% the speed of light. So how can special relativity have anything to do with it? Well, the truth is there are enough electrons in a wire, and the electric interaction is so amazingly strong that even the minuscule effects of length contraction can produce significant charge imbalances that produce a noticeable force.
So special relativity explains electromagnets, but what about permanent magnets?
Yeah, I mean, there can't be electrical currents flowing around inside lumps of rock, can there? Click here to go to Minute Physics, where we'll explore magnetite, compasses, and all the wizardry of permanent magnets.
Okay, welcome back. So hopefully that was enlightening. That sort of explains how special relativity sort of ties in with, well, what we're noticing here is, we're noticing, we've done lots of examples of, where we had a wire. Oh, there we go, a wire with some sort of charge here. And if the wire had a current and there was a moving charge, then by our right-hand rule, we can implement force magnetic equals QV cross B, and you can use a physics gangster sign if you want. It doesn't really matter, and you'll notice that it will exhibit a certain force. So in this case, the B field lines will be like this, so they'll be out of the board. and then the velocity of the proton or the positive charge is to the right, so the magnetic force would be down in this case. And that's what they're describing. They're saying that this exact force, the magnetic force, is not actually a result of a magnetic field. It's actually the result of an electric attraction, because as charges are moving in the wire, the Lorentz contraction, you might remember from high school physics, L equals L naught times 1 minus V squared over C squared. So Lorentz contraction kicks in and the spacing between the charges shrinks, and what ends up happening is there becomes a non-zero charge density as a result of that. There appears to be more electrons per unit of length than there are protons per unit of length. And then Gauss's law kicks in, and then there's an E field, and then there's a force of attraction or repulsion, depending what kind of charge you use. So that's a really cool outline of, and a really cool viewpoint of how magnetic fields are actually not different. They're just an electric field from a different viewpoint. And that also explains, it's a more conceptual understanding of why when you have an electromagnetic wave, you have both an electric field and a magnetic field, because it's not really both, it's just they're the same. One is just the other one viewed from a different point of reference. So it confirms our mathematical findings above that say we have to have one and the other one together. They can't be separate. Well, they can't be separate because they're the same. Okay, so enough of the fun abstract nature of electromagnetism. So we are going to move on to the mathematical representation of an electromagnetic wave. So we know a wave. Let me draw this in black. Let's say the y-axis, the x-axis. We know from basic math, I guess, high school math even, and then grade 11, then grade 12, and then first year. This is a sine wave, for instance. I could have easily drawn a cosine wave, it doesn't really matter. And this sine wave, y is a function of x, can be represented as a sine kx. And you might remember from math class that k is going to be 2 pi over the period. This is introduced in grade 11 when you do transformations of functions and you talk about the Ferris wheel going up and down, the tides coming in and out. And, grade 11 math was a nightmare for a lot of people because, it just historically is. Anyway, so that's where that's introduced. And k is a measure of what we call the spectral period or the spatial period. So it's related to the physical period. So this here would be considered the period. So for a sine graph, y equals sine x, the period is 2 pi. An example other than that would be something like y equals, let's say, sine of 3x. Well, what's the period of this graph? The period of this graph is going to be 2 pi divided by k, which is 2 pi divided by 3. So in this case, this would be 2 pi over 3. Now, in math class, they tend to use capital T for period. In physics, we tend to use the period of a physical wave. We call that wavelength. We call that lambda in physics. So in physics, we say the distance of one oscillation, we call lambda, the wavelength. So I could actually just say 2 pi over lambda. But it's the same idea that you were taught in math. Okay, now that's fine and dandy. I do want to emphasize this is a stationary wave. Oops, not wave, wave. Now, in real life, that would be amazingly cool. That's literally like, having a wavy surface that's just permanently a wavy surface. As time goes on, the wave doesn't change. It's just there. And depending where you are along your x-axis, you either are at a crest or a node or an anti-crest or a node, right? It's a function of space and only space. As time goes on, it's the same object as before. However, what if you take this wave, but let's say 1 second later, the wave shifts forwards. So let's call this the same wave 1 second later. Well, if I used to be here, let's say this is, I don't know, half a second, or no, let's say half a meter, let's say. Well, if I was a half a meter in, my amplitude would be, or my y coordinate would be, I don't know, let's say 1, right? It's a maximum, okay? However, if the red wave is a shifted version, a horizontal translation, a shifted version of the wave, then if we were at the same location in space at 0.5 meters, then I'm no longer at an altitude of 1. I am at an altitude less than 1. So clearly time is also now a secondary variable, because the wave is not only a function of location, it's actually a function of how much time has passed. It's like cars driving. You can cross the road when there's no cars coming. You know, you are physically inhabiting the same space that a car used to take up a moment ago, but after the cars pass, you can safely cross. So it's both spatial and temporal. So when there's sort of these two ideas mixed together, I'll say this is a time dependent. When you sort of have these two objects, or these two dimensions, we call this, we lump them together, and we call this a spatio-temporal wave. Spatio-temporal means a function of both space and time. And you may have heard, I don't know, in sort of physics mumbo jumbo online or something like that, in context of relativity, you may have heard like the fabric of space-time, or the space-time continuum, or like I'm sure you've heard the phrase space-time before. I mean, it's an important idea, but don't be confused. Really, all that really means is space-time, it's just spatio-temporal. It just means it's a function of both location and time. Things change both depending on where you are and how much time has passed. That's all it means, spatio-temporal, that's all it means. Now, in terms of math, well, we already have this notion of y being a cos kx, but if we shift the wave with time, as time goes on, mathematically, all you're doing is a horizontal translation. Horizontal translation. Well, in math, how do we represent horizontal translations of functions? Well, we subtract some function. Well, we'll say, let's subtract a constant for now. Well, if you subtract a constant, what does that do to a cosine graph? It shifts it left or right. So if I subtract something, it'll actually shift it right. If I add something, it'll shift it left. So here you go. The question is, what is that something? We know that something will shift the graph horizontally. The question is, what is it? Well, obviously, as time goes on, the wave is moving forward. So the more time that passes, the larger this horizontal shift should be. So the thing that we're putting there should be a function of time. So the answer to that is omega t. And you've seen this in 136, omega t. Well, if you recall for 136, we know theta equals, well, actually, specifically, we know omega equals theta over t, right? This is analogous to v equals d over t. So that means theta equals omega t. So omega times t is how many radians the wave has traveled through for a certain length of time, t. Well, we are looking for radians because it's cos of something, cos of an angle. So the input, the domain of cos is radians. So we are looking for a quantity that has radian measure. Oh, what happened? Oh, there we go. So we say, therefore, we say our magnetic field is a function of space and time, x and t, and it can be represented as an amplitude. Let's call it b naught. We can say cos kx minus omega t, for instance. Okay. Now, I think this lecture slide chooses to use sine instead of cos. No big deal. They're just shifts of one another. In fact, if you have a sine wave and you have a cosine wave that is shifted, so let's say this is a shifted cosine wave, then they actually become negatives of each other at some point. So what you can do is you can actually factor out a negative sign here, and if you shift it properly, you can turn it into a sine graph pretty easily. My point is, I don't want to dwell on the math details. My point is, it doesn't really matter whether you represent it with a sine wave or a cosine wave, because they're just shifts of one another. So it really doesn't matter. So you could easily set it up. You could easily set it up like this. This is okay. Or if you don't like using cos, you can use sine. It really doesn't matter. Okay, so here is the mathematical representation of the electric field and the magnetic field that oscillate together. And because we know they oscillate together, we know they're both going to have the same spatial frequency, k, and the same angular frequency, omega. And you might remember both from math and both from earlier in physics, physics 136. Oh, let me just insert some space here. How do I insert space? And I'm going to have to click it twice because I always have to click it twice. Okay, so just so you remember, in math, you have the k value to be 2 pi over period. And in physics, the period is a lambda. So you could say that k equals 2 pi over lambda, which is where this comes from. And similarly, with the other one, we have omega equals 2 pi over, and we'll say the period, and this is the period that's actually time. Oops, this is the period that's actually time. And we could do that. We could say, what's the period of the wave? Well, it's 2 pi over omega equals the period of the wave. The other thing is we don't really look at periods of waves. We look at the frequency of the waves. And we know frequency and time are inverses of one another. So we can actually say this is actually 2 pi times the frequency, because 1 over period is also frequency. And that is where this comes from. And this is a relationship that is between omega and k. And the relationship is always the speed of light, c. So that's a really important or not necessarily c, the speed of light in the material. If you're looking at an electromagnetic wave in water, then it won't be c. It will be the speed of light in water, whatever that happens to be. It'll be still pretty large. It just won't be c, so to speak. The way you get this is you say, okay, v equals f lambda. This is what in first year, this is what we call the wave equation. And physicists do not actually call this the wave equation, but nonetheless. The speed is going to be c equals f lambda. So if you plug in f, we know f is going to be omega over 2 pi. So this is going to be omega over 2 pi. And if you plug in lambda is going to be 2 pi over k. And if you simplify, 2 pi And you're going to end up getting omega over k equals c, which is exactly what that equation is. Okay, so these are the tools that we use. We know how to mathematically represent a wave now, and we also know the relationship between the quantities in the equations, omega, k, E naught or E maximum, or B naught or B maximum, the amplitude. We can relate these quantities to more physical attributes of the wave, like frequency. And we know from before, the frequency of the wave, or the wavelength of the wave, governs, where is it here? Governs, say, the color that you see. So, you know, in a question, and we'll do a question very shortly. If we do a question and they talk about, oh, we've got green light. Okay, well, green light is, you know, around, what, 525 nanometers. Or it's a range, but you know what I mean. Well, if you know what the wavelength is and you know what the frequency is, then you can come up with your omega and your k value, and that gets you most of the mathematical representation that you need for your answer. Okay. Now, I mentioned before, we have this sort of right-hand rule nature. The wave is propagating forward with time, and the direction of this propagation is, again, I'm a left-handed person. As you can see, I'm holding the stylus in my left hand. So physics is very annoying for me because the right hand is so very popular in physics. So yet again, we have a right-hand rule. And we covered this yesterday, but just so you know, you take your fingernails and you point them in the direction of the electric field, and then you curl them in the direction of the magnetic field, wherever that happens to be. And then your thumb points in the direction of propagation. Okay. So here, this slide is showing, you know, a very similar thing to the previous slide. But again, if you apply the right-hand rule, right hand, fingernails in the direction of the E field, so fingernails are pointing up. Curl your fingernails in the direction of the B field, so curl your fingernails this way in the direction of the B field, and your thumb is in fact pointing backwards. So this is saying, it's deceptive, because when you draw the X, Y, Z coordinate system, it's deceptive. We trick your brain into visually thinking the wave is traveling this way, right? Just based on how we drew it, but that's wrong. If you look at the right-hand rule, you see that the direction of the propagation is in fact backwards, because your thumb will be pointing backwards. So we can do an example here. So here's an example. A carbon dioxide laser emits a sinusoidal electromagnetic wave that travels in a vacuum in the negative X direction. Okay, so we're told which direction it propagates in. That's going to be important. So it travels to the left, right? If you draw your XY, then we can call this the sort of negative direction. We call left the negative direction. So if you're thinking about translations, horizontal translations in math, remember you subtract the constant to move it to the right, and you add the constant to move it to the left. Remember that? So it depends which way you're traveling. So I'm going to highlight that in the question here. The wavelength is known to be 10.6 times 10 to the minus 6 meters. And the E field, the direction of the E field is along the Z axis with a maximum magnitude, oh boy, so I'll just say E max equals 1.5 times 10 to the 6 volts per meter in the Z direction. Okay, so I did that. Find the equations for the magnitudes and vectors of E and B for the functions of time and position. So what are we looking for? We're looking for B of xt and we're looking for E of xt. Okay, so here we go. We know the formula. The formula is going to be B. This slide likes to use sine, so we can use sine. It's no big deal. Omega t plus or minus kx, plus or minus depending which way it's propagating, left or right. And E is very similar. Oops, not B. E sine omega t plus minus kx. Okay, so what do we know? What do we need? Well, we do know that E max is in the z direction. So this is going to be in z hat direction. And with our right-hand rule, we also know it's traveling to the left. So the z-axis in this diagram, I guess, would be coming out of the board here. So if the E field is in the z direction, this is the E field, and the direction of motion is in the negative, come on. The direction of motion is backwards, then your thumb has to point backwards, your fingernails have to start pointing out of the board, which makes the B field, point upwards by the right-hand rule. So these two pieces we knew, and we were able to infer the direction of the B field using the right-hand rule. So the direction of the B field we know is going to be in the Y direction. Okay. I don't think they didn't ask, oh, they just asked for the magnitudes. Okay, they only asked for the magnitudes, they didn't ask for the directions. Who cares? Now we know the directions. It's an extra layer of knowledge for you or practice for you. Okay, what else do we need? Okay, well, we need, we have E max. We have E max stated in the question. E max is 1.5 times 10 to the 6. That was given to us in the question. What else was given to us in the question? Lambda. Lambda was given to us in the question. Well, we know that K equals 2 pi over lambda. So we can actually say, okay, K is actually going to be 2 pi over lambda x, 2 pi over lambda x. All right. And we're also told that it's traveling in the negative x direction, like backwards. So that tells me in terms of grade 11 math with transformations of graphs, we do not subtract the constant because that would move it to the left. Sorry, we don't subtract the constant because that would move it to the right. We add the constant because that would move it to the left. So let me get rid of these. We are told that they travel, oops, sorry. We are told that they travel direction, direction does not start with B, direction of travel is left. So we add the constant. And then the only thing that's left that we really have to figure out is omega. We don't know what omega is. So we look at our equations, we know omega equals 2 pi times the frequency, right? That's true, but we also don't have the frequency. Well, our other equation that we have is that the speed of light is going to equal omega over lambda. So with these two equations, we should be able to sort out what we need that way. So omega is going to equal lambda times c. And we have lambda in the question. So I'd say, therefore, the electric field as a function of space and time is going to be 1.5 times 10 to the 6 sine lambda times c. What was lambda? Lambda was 10 times 10 to the minus 6. So that's like effectively 10 to the minus 7. Well, it's kind of 11. So we'll say 1.1 times 10 to the minus 7 times 3 times 10 to the 8 time plus 2 pi divided by 11 times 10 to the minus 6 x in the z hat direction. Let me just move this over here. Okay, and where does that leave us for B? Well, the B field, well, we need to know Bmax. Bmax is scaled. We learned this last time. Bmax is scaled with this equation. So E max over C. So this is going to be 1.5 times 10 to the 6 over 3 times 10 to the 8 sine. It's going to be the same thing here now. 1.1 times 3. That's going to be 3.3 times 10. So that'll be around 33. Now in reality, that wasn't really 1.1. It was what, 10.6? So this would really be, I think 10.6 t plus, now 2 pi is around, I want to say 6. This is, let's see here, this is 10.6. That's what, 2 pi over 10.6, divide everything by 2, you're going to get pi over 5.3. So 3 over 5 is around 60%. So 60% times 10 to the minus 6 is going to be 6 times 10 to the minus 7x. And this is going to be in the y hat direction. Oh no, that's minus 6. So this is going to be minus 5, plus 5. Sorry, I did that wrong. This is going to be, yeah, 0.6 divided by 10 to the minus 6. So that's minus 1 plus 6 is plus 5. There you go. So without a calculator, oh, this is, did I do that math wrong? I think I may have done that math wrong now. Well, whatever that happens to be. Omega over lambda, they're getting, what are they getting here? Times 10 to the 14. Where are they getting that? Omega equals C. Oh yeah, it's not lambda, it's K. Right, I got the equation wrong. It's not lambda, it's K. Sorry, yep, that's right. And that is going to be omega over K. K is going to be 2 pi over lambda. There we go. There we go. That makes much more sense. So then if we're solving for omega, omega is going to equal 2 pi c over lambda. There you go. So this is going to be around 6 times 3 times 10 to the 8 over 10 times 10 to the minus 6. So let's see here. 6 times 3 is around 18. That's around 20. 20 over 10 is around 2. I'm approximating here. And then 8 plus 6 is going to be around 14. So without a calculator, and I know I'm also approximating 2 pi to be 6, which is an approximation because I don't have a calculator on me at the moment. So I'm getting around times 10 to the 14. It looks like if you use a calculator, oh yeah, looks like they are getting it. They're getting 1.78 times 10 to the 14. I was getting 2 times 10 to the 14. So yeah, I was close. And I was getting 6 times 10 to the 5 for this value. They're getting 5.93 times 10 to the 5 for that value. So it's reasonably close. And hopefully that was also, it showed you sort of how to, or remind you how to ballpark or approximate numbers without a calculator. Because calculators really slow you down, and brackets, and you always get it wrong, and you always have a love-hate relationship with your calculators. So I don't know, I would strongly recommend practicing this sort of, not mental math, but sort of approximation math. Makes math people crazy, but physicists love it. So anyway, there's your answer. Oh, I guess we never did this. Sorry, this one here. That is going to be 1 over 2, and so 0.5 times 10 to the 6 minus 8 is going to be minus 2. So this is going to be what, 5 times 10 to the minus 3. So the coefficient there should be around 5 times 10 to the minus 3. Is that what they had? Yeah, they had 5 times 10 to the minus 3. So there you go. So that's pretty much all there is to the electromagnetic waves unit. We were talking about, let's just jump back up for a second to the learning objectives, just to sort of summarize. So to understand the electromagnetic waves, the speed of light, and the electromagnetic spectrum. So do we understand electromagnetic waves? Well, we explained that they are in fact an oscillating electric field with a coupled oscillating magnetic field that are oscillating together. And we also took it a step further. We looked at Maxwell's equations and how Maxwell's equations showed that the electric field and the magnetic field were coupled together in the event that they are sinusoidally oscillating. The speed of light, we looked at the speed of light. If you recall from yesterday's lecture, was 1 over root mu epsilon. And this explains that when you're in a different material is going to have a different mu value, a different material is going to have a different epsilon value. So that's what modifies the speed of light in a different material, such as water, for instance. And yesterday we talked about the electromagnetic spectrum, radio waves, microwaves, infrared waves, visible light. UV light comes from the sun, X-rays, which we can use to look at our bones, which is very prolonged exposure is very bad. And then above X-rays is gamma rays, which are absolutely deadly. That does not produce the Hulk. It does, it would have killed Bruce Banner. I don't know the fiction that it produced the Hulk. Anyway, characterize sinusoidal waves. We learned how to characterize them. We learned how to represent them mathematically. As a spatio-temporal wave, it's both a function of location x and how much time has passed t. And we looked at the properties of those, that the spatial component has an angular frequency omega, and the temporal component has an angular frequency omega. The spatial component has a spectral frequency k, and they're related to both the frequency f and the lambda. So we looked at those as well. We looked at the right-hand rule to sort of predict the direction of propagation as a function of direction of E and or B. And we governed or explained reflection and refraction and polarization in the previous chapter. So if you look at the goals for this chapter, we have pretty much hit all of the goals in this chapter. The thing I'm choosing to cut out is energy in the electromagnetic wave. I've included the slides here just for extra information in case you care. It will not be reflected on the exam. So at least it shouldn't be. As you should know by now, we're using multiple choice question banks for the exam or for all the assessments. And technically this is part of the electromagnetic chapter, even though I'm choosing not to teach it in depth. So I'm going to show, I put slides here to show you, if you do happen to get one of these energy questions on the exam, you can either send me an email or post something on Piazza, but ultimately let me know at some point, even if it's after the exam is over, that you got an energy question, and I'll go back and I'll make sure you get the marks for that. But most of the questions are fairly easy, so I just want to show you very, very, very briefly kind of what the equation is, and then maybe it'll just be easier for you to answer it, maybe, than to deal with the aftermath of having to get around it. So very, very quickly, you must know that light has a certain intensity. You can have bright light, you can have dim light, blah, 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 blah. And that is a measure of how much energy is in the wave. And the way in which you can measure the energy in the wave is you literally add up the energy in the electric wave, and then you add up the energy in the magnetic wave, and you can relate them two together. And it turns out when you simplify, the total energy in an electromagnetic wave is going to be epsilon naught times the magnitude of the electric field squared. And the reason we can do this and represent it only in terms of the electric field is because we know there's a relationship between the magnitude of the B field and the magnitude of the E and B field, specifically this relationship here. So we can swap out B in terms of E, and then our answer for total energy is only in terms of E. Now, if you're prejudiced against the E field and you want to represent the total energy in terms of the B field, knock yourself out. Absolutely no problem. Okay, so if you do get any energy questions with electromagnetism in the exam multiple choice, and if you do, it'll only be like one of them at most. This is likely the equation that you're going to need for it. But again, don't stress about it. If they happen to wiggle their way through, just shoot me an email after the fact. I don't want you wasting your time during the exam trying to send me an email about it. Do it after the fact, and I'll take care of it for you. Okay, in terms of material, that is all of the material in the course. I was able to find one last picture. If you recall yesterday, I was talking about how James Cameron's Avatar was the first 3D movie that had the new sort of glasses that were not the red and green 3D glasses. I found a lecture slide that sort of illustrated what I was describing yesterday. So before we move on, I kind of want to show you. Here, if you have polarized sunglasses, for instance, you don't even have to go to a 3D movie to get these, but most sunglasses now are quote unquote polarized, and they're meant for anti-glare and things like that, and they're helpful. But if you have a pair of sunglasses and let's say another family member has a pair of polarized sunglasses, they have to be polarized. Those are generally the more expensive ones for no good reason. It costs them maybe 10 cents extra to make them polarized, and they charge you an extra couple $100 for it. Crazy. Anyway, if you take them and you rotate the two pairs of lenses relative to each other, you can see how light, light can pass through the non-overlapping bit, but where you overlap them, it's completely pitch black. And you can change the angle to which these are relative to each other, and you can change how much light is allowed to pass through. So if you have multiple members of your family in the same household and they happen to have polarized sunglasses, I encourage you to go out and ask your family members if you can borrow them for a few seconds and try this out for yourself. It's actually a very good way to figure out whether or not you have polarized sunglasses. Because if you have non-polarized sunglasses, it wouldn't do this. So anyway.
I'm also going to interrupt for a second.
I'll take a giant deep breath, and that is the entire curriculum for Physics 137. As busy as this has felt, we had, I think, 3 fewer chapters this semester compared to 136. And so that really made 136 a sprint. We were really moving fast in 136. 137, we were also moving fast, but we were in fact moving slower than the previous course, even though this has felt fast. So I just want to really thank everyone and give you a good pat on your back. I mean, an accelerated class is really hard at the best of times. And this is an accelerated physics class, no less. And in physics, we need to teach the physics. And, there's a lot of math background that we assume students have coming in. And, math from high school that you may not have seen a while, vectors, dot products, cross products that you've seen in grade 12 MCV for UO, which may have been a while for some of you guys. And, it was such a sprint. And even taking physics in September and January, that's hard enough for students taking it at the regular pace. So for anyone now who is presently in the lecture, you've made it to the end of the class. That alone, regardless of what your standing is, good marks, bad marks, or what you think are bad marks, regardless of where you are, you all deserve a huge round of applause for making it, especially for those of you who also took 136 in addition to 137. You guys especially deserve. I'd give you a good handshake, but COVID is not the right time to give you a hearty handshake for that. But I just wanted to, you know, make sure that you guys were aware that anyone who's still in the class is well deserving of you know, respect and admiration and perseverance, because it was a long, what felt like a long time, and definitely a lot of work, blood, sweat, and tears. So, you know, congratulations all of you for making it. So we're going to shift gears. I'll give you guys maybe a 5 or 10 minute break. Maybe we'll come back. Well, let's say we'll come back at 2:30, and for the remaining half an hour, we'll do some practice questions for the wave nature of light unit. I've pulled out some multiple choice questions that we can talk about.
Hey, Mark, before you get going, can I add something with the polarized lenses?
Oh, yes.
So another way to check if your lenses are polarized is a lot of like computer screens. So like your smartphones, tablets, laptops, things like that. Those will also have a polarized screen. So it'll be darker depending on which way you tilt your head while wearing the glasses. So that can be mildly annoying. On top of that, if you try the you know, putting the two lenses on top of each other with the 3D glasses that you get from the movies, depending on how you do it, you might get some weird, funny, unexpected results because those lenses are radially polarized rather than linearly.
Yeah, yeah, I think they're circularly polarized or something. Yeah, you're right.
Yeah. So, yeah, I know my phone screen is actually diagonally polarized, so you can look at it portrait or landscape with polarized lenses, and it still works, which I thought was brilliant.
Yeah, well, I mean, that is a good design. But yeah, it's a good point. I don't wear glasses or sunglasses, so I never really see. You're right. There are lots of computer screens that are polarized, but because I don't personally wear glasses, I forgot, because I never have to look at a computer screen with polarized glasses on my face. But for those of you who, even if you don't have sunglasses, even if you have eyeglasses, quite often you can get those polarized as well to help reduce glare. And again, I don't experience this because I don't wear glasses, but for those of you who do wear glasses, you may have experienced what Romina's describing, where you're looking at your computer screen, and if you look at it sideways, it looks a little darker. And that's a result of the polarized lenses on your face. Okay, well now it's 2:24. So let's come back at 2:34. We'll give you a good 10-minute break, and we'll do some practice problems in the wave nature of light, and that'll take us to the end of today's lecture. Okay, so we'll take a brief pause, and I will see you guys in about 10 minutes. Ciao for now.